thank you everyone for attending the session. It's a pleasure to be able to tell you about my program and opportunities that you might be able to take advantage of for some technical assistance and funding. As Greg said, my name is Sam Anderson. I'm the energy specialist at the Colorado Department of Agriculture, and I'm the administrator for the ACRE3 Energy Grants Program. Let me start sharing my screen here. Okay, got that? Great. All right, the ACRE3 program stands for Advancing Colorado's Renewable Energy and Energy Efficiency. We provide funding and technical assistance to farmers and ranchers to help you modernize your equipment and reduce your energy costs. Over the past 6 years or so, we've completed about 133 energy projects on farms across 24 counties in the state. These projects have totaled about almost $5 million in value, and we brought in about $1.9 million in additional assistance and provided about $1.3 million of additional assistance from my program. Some of that was in-house services as well. Since just for this year, the projects that we have in motion right now include about 600 kilowatts of renewable energy production, about 1.7 million kilowatt hours per year of energy savings on farms, which equates to about $175,000 in annual energy savings for those farmers. And that offsets about 1,600 tons of carbon dioxide equivalent emissions. So what does the ACRE3 program bring to you? What is our value? As you know, in Colorado, agriculture is our second largest economic sector, with a total impact of about $47 billion per year in this state. That includes more than $440 million per year of direct energy costs. Out of that $440 million a year, about half of it just represents the cost of pumping water for irrigation. And up to about 75% of those irrigation pumps are operating well below their performance specs. And so there's a lot of work that we could do to upgrade those pumping plants alone to save potentially about $80 or $90 million a year. Sorry, let's see, is that right? 80 or 90, well, $8 to $9 million per year in energy costs, 80 to 90 million kilowatt hours per year in energy. But the problem is, historically, farmers and ranchers have never really had good access to qualified energy service providers to help them with these projects. And the existing equipment providers don't always provide the kind of services necessary to do energy audits and provide access to the state and federal funding available to help with these projects. So as I mentioned, just through energy efficiency and just with irrigation systems alone, there's a potential of about 90 million kilowatt hours per year of energy savings. That's about $8 to $9 million or $8 to $900,000 per year. Or, sorry, let's see, 90 million kilowatt hours, let's say 10 cents a kilowatt hour, $8 to $9 million per year. Sorry about that. And so potentially about 10 megawatts of renewable energy potential associated with those systems in, for example, photovoltaic systems connected to those pumping plants. We also identified about 40 megawatts of hydropower potential at non-powered agricultural dams, about 30 megawatts across irrigated fields in Colorado, where we can integrate hydropower with center pivot, for example. And then we identified a couple of hundred locations in Colorado that have strong technical potential to install hydropower in canals where there's a short drop in the canal. Our strategy then in this program is, first of all, to understand what on-farm needs are and target those needs. So we commissioned a series of reports along with the Energy Office about 8 to 10 years ago that identified market opportunities. We've performed an agricultural energy market study and some focused studies on hydropower potential in irrigation systems and irrigation canals and dams, and also looked at various renewable energy opportunities in agriculture. So our focus is on agricultural producers and giving money directly to them to incorporate these energy efficiency and renewable energy practices to reduce their operating costs. And then we provide the technical assistance along with the funding to help them implement those projects and leverage federal dollars. So in many cases, we can stack the funding from this program to stack that together with funding, for example, from rural development or from NRCS for the same projects. We have a lot of stakeholders in this program, and the USDA currently provides the majority of the funding for the actual projects that are identified through the energy audits and feasibility studies that we do. And that complements the additional funding for projects that the ACRE3 program provides. In addition, the Colorado Energy Office is a primary program partner, and they provide free energy audits to any farmer or rancher across the state who meets some minimum requirements for on-farm energy consumption, not including energy fuels used for off-road vehicles. Of course, our customers are farmers and ranchers, and we coordinate our services together with many agricultural associations, with the conservation districts, ag extension, and various others to help coordinate all of our activities as well. So I'm just going to talk a little bit more about our process, and then we'll dive into hydropower. But I want to give you an overview to see how this program works. So phase one essentially provides the energy audit report if it's an energy efficiency project, or the feasibility study for renewable energy projects. And from there, we use those studies to then apply for financing for the project, whether it's grants or loans or some combination. And then in parallel with that, we provide technical assistance to help the agricultural producer coordinate the contractors and go through the process of installing the project. We work with a lot of different funding sources in addition to the grant funding available through this program. We can provide grants, as you see there in the yellow text, of up to $100,000 per producer. And the NRCS may fund up to $250,000 per contract. And then rural development can provide grants as well, sometimes in excess of $250,000 for projects. They will provide up to 25% of the project cost. Then there are some other creative financing opportunities that we work with. One is a program called CPACE, which many of you probably haven't heard of, but I'd be glad to answer questions about those if you're interested later. So I mentioned that we can provide up to about $100,000 per applicant. We have about $500,000 per year in total available on average. We accept applications quarterly, and in some circumstances, that money can be stacked, as I mentioned, with federal funding. It can always be stacked with any utility rebates or other funding sources as well. And typically, we fund about half of the project cost. If that money is stacked with a REAP grant, for example, in some situations, we can pay for as much as 80% of the total project cost in the combined funding. This year, we have a bill that would provide stimulus funding from the state for this program in the legislature right now. It's currently in the Senate Agriculture and Natural Resources Committee, and they may be voting on it this afternoon, maybe in the next couple of hours. If this bill passes, it would provide $3 million for this program, with the big catch that we have to spend all this money. It has to be out the door by the end of June next year. So that means we have to identify some very quick projects. And one of our strategies that we hope will work for us to do that is to spend about half of this on irrigation hydropower projects. But those projects usually take about 2 to 5 years to complete, from initially identifying the project until we get the funding lined up, do the feasibility study, do some engineering, and procure all the components, get it installed, and then finally pay it out. We only have about 10 to 12 months to really do the project. So we think that if we can do some quick pipeline projects that would get everything in place to do the associated hydropower projects later on with assistance from NRCS, that could be a good fit for the program funding here through this bill. Another opportunity to do quick hydropower projects is wherever there's a large pressure reducing valve on, say, some center pivot irrigation. We can put a hydroelectric turbine in parallel with that PRV and recover that energy instead of just dissipating it and losing it through the PRV. So I want to give you some quick examples of the range of different kinds of projects that we fund in this program, and just talk briefly about that, and then we'll go into the hydropower. So our agricultural energy initiative is one of our 2 initiatives, the second being hydropower. And we've done many projects. There's about 40 different kinds of project types that we fund through this program. Many of them are in greenhouses. Some of them are in dairies, irrigation pumping plants, as I mentioned, insulating shop buildings on farms. In the picture on the top left, for example, those white tiles on the wall are a type of energy storage material that's only about an 1/8 inch thick, but it's a phase change material that will melt and turn solid to absorb and release heat throughout the day, and in that way it modulates the temperature swings in the morning and evening in the greenhouse. In addition to hydropower, on an irrigation pumping plant, we can help to fund upgrades to the motors, upgrade from a 50-year-old motor, for example, that's operating at 60 or 70% efficiency up to a 90% or 95% high efficiency motor. Maybe add a variable frequency drive to that system, and possibly replace the well pump as well. And then we can tie that system together with solar through net metering, so that even if the solar is not operating, not providing any energy, the irrigation system still operates as whether the solar is there or not. And the solar just builds up energy credits through the year that offset the operating costs for that pumping plant. Another type of irrigation project that we did this past year was this project in Craig. And this farmer was pumping water out of the Little Snake River with a diesel pump. And just by rerouting his pipeline to the center pivot and buying a more efficient pump, we were able to reduce his fuel consumption by about 50%, which is more than 1,400 gallons per year of savings. So we really improved the profit margins for this farmer in that area. So we reduced the size of his pumping plant from 158 horsepower to 75 horsepower, and he still gets the same performance out of that system. All right, so I'm ready to dive into hydropower. And so there are initially, there are two different kinds of systems that we do: hydroelectric and then something we call hydromechanical. And each of these projects have a number of other conservation goals and priorities associated with them. So for example, we prioritize soil and water quality and land and resource stewardship. We also have a goal of modernizing irrigation infrastructure. When the situation is right, we can upgrade from an open earthen ditch to irrigation pipeline and improve the water flow rates across the crop. We prioritize low impact hydropower, which I'll talk about more in a moment. And then with hydroelectric, as I mentioned, we prioritize net metered systems. So our stewardship goals include salinity reduction. As many of you might be aware, in Western Colorado, wherever we have the Mancos Shale, it used to be an ancient seabed. So salinity is a big problem in the upper Colorado River Basin. So salinity reduction is an important goal for this program. We also emphasize erosion reduction when we can, and tailwater pollution as well. So anytime we can reduce overflow from flood irrigation, for example, by converting to a center pivot, and reduce the tailwater that might be carrying fertilizer or pesticides, that's a big priority for this program as well. And then water efficiency improvements when it's appropriate. So these are a couple of pictures. That cliff there shows erosion that has occurred in this ditch over the past 100 years or so near Crawford. And you know, by converting to center pivots, sometimes you can eliminate the standing water like this. That is one of the main reasons why salinity becomes a problem on these fields. So what is low impact hydropower? This picture represents a perfect example. So here's, let's say, a farmer who converts his irrigation ditch to a pipeline, and he's got a lot of excess gravitational energy in that pipeline as the water falls from the head gate down to where the center pivot is. Let's say he has about 50 pounds of pressure, and he needs 30 pounds of pressure for his center pivot, but he has this extra 20 pounds of pressure, which is like 75 feet of head, that he needs to dissipate so he doesn't flow out the nozzles on his center pivot. So he puts in this maybe $10,000 or $15,000 PRV, and it just dissipates all that energy. Well, that's quite a few kilowatts of power that has value. And so if we just put a turbine in parallel with that PRV, we can recover that energy and make use of it and recover the economic value from that, the energy in that water. But low impact hydropower is also about using existing infrastructure, as in the example I just mentioned, not changing in any significant way how that water is distributed, so not changing the water rights in any way, and ensuring that there are no adverse effects natural resources or habitat, cultural things of cultural value, or maybe even like the outdoor recreation resources. So hydropower can be very cost effective. And so I put together some graphics here to show you what kind of value hydroelectric power can provide. So a typical household in Colorado uses about 9,000 kilowatt hours per year. And to meet this, you could either install on your rooftop a 6 kilowatt solar photovoltaic system, or you could generate the same amount of energy with a 1.5 kilowatt hydropower system. So the difference is that solar is only producing energy during daylight hours, and it's typically about 5.5 hours a day of full production throughout the year in Colorado. Now, the actual production is much lower in the morning and much lower in the evening, but when you average everything out, it's full production for on average 5.5 hours per day. Whereas hydropower could be producing for 24 hours a day if you have a year-round source. You're producing at least 4 times more energy per year than you would be producing for the same size solar array. I hope that makes sense to you. So how does the cost compare? Well, solar is about half the cost, though, of a small scale micro hydro system. So an 8 kilowatt system might be about $2.50 a watt, about $20,000. A 4 kilowatt system costs $5 a watt, but so it's the same project cost, but potentially producing more than twice as much energy if it's operating year-round, or if it's in an irrigation system where the irrigation water is only available for maybe 5 or 6 months a year, then it's producing about the same as that 8 kilowatt system. So those costs are not directly scalable, and they go down dramatically as the size of the system goes up. This little plot in the corner is a bit outdated because today for solar PV, rather than $3.50 a watt, it's actually down competitive with any of the energy sources on this plot. So it's actually, in some cases on large scale projects, running about $1 to $1.25 per watt. So hydro is very competitive at large scales. Here, second from the left, and but this plot I think is about 7 or 8 years old, and since then solar has come down, at least for the equipment, reduced about 80 to 90% in cost. So it's a pretty dramatic reduction in cost. We completed a market study of hydropower across the state in 2013. And we looked at 3 different categories. One is the potential on individual irrigated fields across Colorado, and that identified 5,000 irrigated fields with technical potential for hydropower. We also looked at canal drops and agricultural dams that I mentioned before. Of the 5,000 fields that were identified in this study, about 87% of that is currently flood irrigated. And so to access that hydropower, it means converting the flood irrigation into pipelines and center pivots. Hydroelectric systems can, because they're net metered, they will operate independently of the sprinkler drive system. So even if the hydroelectric system for some reason has to be disconnected for servicing or shuts down for some reason, there's normally still electricity to service the center pivot and keep it operating even without the hydropower system. Most utilities in the state, most of the co-ops, have a cap for irrigation hydropower, maximum size of 25 kilowatts. But there are a few like Delta Montrose Electric that will allow up to 50 kilowatts for the maximum size of on-farm hydro. And in some cases, there are no caps. So if you've got 100 or 150 kilowatts of potential hydropower capacity, then we could develop that full capacity. And we have looked at a number of projects like that. This is a project just south of Greeley, Colorado. It's a 25 kilowatt system. We provided assistance for this in 2016, and it's been running for about 3 years. It produces more energy than we anticipated. This type of turbine is called a cross-flow turbine, and it's a very efficient turbine that works really well for low flow. In this case, on this ditch, the farmer only has about 60 feet of drop across about 400-foot length of this ditch. And that's enough for him with his flow rate to produce about 25 kilowatts. And I just want to point out real quickly, sitting on that blue cabinet for the turbine is a nickel on its edge. And Jim Park, the owner of this project, is very proud that this system is built so well that even when that's operating at full capacity at 25 kilowatts, there are absolutely no vibrations in the system, and that nickel will still balance on edge. He designed and built the whole powerhouse himself. He poured all the concrete for the foundation, and installed the powerhouse and did all that himself. He just needed somebody else to put in the electronics and the equipment for him. He's very proud of that. This is a project in Hotchkiss, Colorado, one of our first projects as well. This one, each of these turbines here is 4 kilowatts. So 8 kilowatts is enough on this farm to offset the operations for 3 center pivots and a veterinary hospital on the property. So this type of turbine is called a turbo turbine, and these are like spoons, and these 4 hoses on each one, each has a nozzle that shoots a very high intensity nozzle, a jet of water into these spoon-like structures on the runner here in the turbine. This one uses a solar inverter. There are actually 2 solar inverters here that convert the direct current power from the turbines, from the generators that are sitting on top, into alternating current to match it with the grid, and then puts it on the grid. These devices that you see in the back here are load diversions. If the grid if there's a blackout and the grid goes down, we don't need to put in any equipment to turn off the water to the turbines. The turbine can keep running, but then the inverter has a shunt in it that diverts the electricity into these devices. And basically it's just some electric water heater elements in open air, and they burn off all that electricity, literally. And it's designed safely to meet electrical codes and safety codes, and it's a fairly common and low cost way to manage the energy production from these systems to meet the utility requirements. This is a larger hydro project that we did in the town of Meeker with the White River Electric Association. They have a 167 kilowatt turbine that they put in on an irrigation ditch that runs across this bench here. And the original pipeline at the end of the ditch hangs above the highway here. And so they just added another pipeline underground that runs to the turbine here. And so they're generating 167 kilowatts of energy and of power. And then the royalties from that go to the ditch company and is shared among the shareholders in that ditch. So there's another kind of hydropower system that I'd like to talk about for a few minutes. This type of system works really well in remote areas where there's no access to local electric utility lines to put in some electrical motors for a center pivot. We don't need any electricity to run these systems if there's enough fall and gravitational energy in the water that goes to the center pivot that we can run the whole system on the energy in that water. So there are two kinds of systems here. One uses the energy in excess pressure, and you can see in this system the water is going to the center pivot. Part of it is diverted for a short distance, just a few feet, into this water pump that's just installed in reverse. That water pump is connected to a pulley that operates this hydraulic power unit. And this is a TNL irrigation system that runs all the towers in the center pivot run on hydraulic power. So they don't need any electricity as long as there's something to provide shaft power to the drive shaft on this hydraulic power unit. I hope that makes sense to you. So the water that gets discharged in this case comes out of the pump, goes right back into the pipeline and goes on to the nozzles in the center pivot. In this second case, this uses the energy in excess water. So water additional flow is used just to go through that pump and provide the energy for the hydraulic power unit. And then that water gets discharged from that hydraulic pump or the turbine and gets discharged into this ditch, which then goes down to provide water for fields lower down on the same property. Now, if you don't have fields at a lower elevation where you can use that water, that might be a screening factor when this isn't a feasible option for you. So I have a video here. Again, this is that same excess pressure system and just shows a little bit more closely. They're just getting ready to tighten up the pulley system here and start up this center pivot. It takes about 10 minutes to slowly open these valves so that you don't have like a water hammer effect that could damage the components. And so after about 10 to 15 minutes, then it's running at a steady state. But I have a quick video here, and to play this, the audio just shows the sound of the turbine spinning here. And it lasts about a minute, so let me play this for you. But while I do, I have to disconnect my audio and switch to the computer audio. So one moment while I do. Okay, hopefully my audio is back. So I hope that that gives you a general idea of how these systems work. I have a few more slides here, and then I'll open it up for questions. Let's see. All right, so briefly, the hydropower project development process, it can be a little bit complex, but we want to reduce the risks in these projects, make sure that they're really good projects before we give away any money for these projects. So it starts with a pre-application, and then I'll go through a process to evaluate the project, usually just using Google Earth, and figure out the lay of the land and see how good the resources are. And if everything looks good there, then we'll provide about $5,000 for a free feasibility study. There are a few contractors who are not quite able to do it for $5,000, but in most cases, $5,000 will pay for the full cost of the feasibility study. From there, that study can be used to access funding from USDA, whether it's the REAP grant program or NRCS, and also funding from potentially the Water Conservation Board. CWRPDA is the Colorado Water Resources and Power Development Authority, and they provide very similar funding to CWCB. And then we can use that report also for getting the federal permits and everything else that we need for that project. Once that's done, we proceed with engineering and construction, and then after we inspect the project, we can pay out the grants. So do you think you might have a good project? Well, actually, doing a preliminary idea, getting a rough assessment of how much energy you could produce is not very difficult. Here's a little bit of a very simple math equation for you. If you know how much flow rate you have in cubic feet per second, and the feet of fall from, for example, your head gate down to where the center pivot is, multiply those together and divide by 25, and that'll tell you approximately how many kilowatts of power you might be able to produce. So we go through lots of screening to make sure the project is not running into any obstacles, make sure you're eligible for funding. And then the feasibility study will include a preliminary design, enough to get a close approximation of the total project costs. And then we use that estimated project cost and the value of the energy produced to look at the economic viability. And we look for any barriers there, as well as any technical barriers in the project, such as resource constraints. And then the feasibility study will look for any potential fatal flaws that might cause the project to fail at some point. We have an online guide, a navigation guide that will lead you through the whole process of identifying a potential project, doing a self-screening process, then filling out our pre-application, getting the technical report, applying for federal funding. And if you click on each of these symbols on the side, it expands each of these steps into additional instructions and attachments for all the forms that you might need to apply, for example, for the REAP grant or for NRCS funding and so forth. And all the instructions, information, everything you need to know also about federal permitting and so forth. So there's a list of contractors that you can contact, all the information from start to finish, hopefully, that you would need in these projects. So I put in here some information about the current payment rates from NRCS for the hydropower component on these. It's under the practice code 420, if you're familiar with the NRCS EQIP program. So if you have, for example, a let's say a 10 kilowatt hydro project, they'll pay you about $32,000 to help you install that project. A 10 kilowatt system might cost potentially about $80,000. So between the funding from NRCS plus some money from ACRE3, we can maybe provide about $50,000 of the $80,000 for that project cost. Similarly, for a hydromechanical system, if you have let's say a 15 horsepower pump that's necessary to run your center pivot, then you can get about $18,000 for that project, maybe $20,000 for that project. There are a few challenges for these projects in particular. Because of COVID, there have been some big supply chain issues in providing the equipment. You might be familiar with how the costs of steel and pipeline and even the plastic pipe nowadays is 2 or 3 times what it might have cost a year ago. So that's a real challenge. And so we try to compensate with additional funding to assist with those costs wherever we can. I talked a little bit about the cap of 25 kilowatts for most co-ops and most utilities in Colorado. Sometimes we run into some issues where there is a residence on the same electrical meter as the agricultural loads. And so we have to figure out some way to separate those. And the funding from NRCS and from our program will only take the proportion of those loads that are agricultural. And then that's the portion that's funded for these projects. If you want to pay some incremental cost and upgrade the system to a little bit larger and offset all your residential loads as well, that's up to you. And we've done projects like that that are approved by NRCS and REAP and our program, but we don't provide assistance on the funding for that residential portion of the project. Demand charges are a big challenge for us too, because with solar in particular, solar cannot reduce the demand charges. However, with the hydro, since it operates 24 hours a day when the water is flowing, it can have a significant impact on the demand charges. So then, even with our assistance, sometimes these projects are just difficult for some agricultural producers to finance. So with that, let me briefly add that we've done about 8 of these hydropower systems that are operating around the state, and there are 15 more that are under construction now, including 10 hydro system units that together are about 225 kilowatts of total capacity on the Ute Mountain Ute Reservation in Toyac, Colorado. And I'll be glad to open it up for questions.
Thank you, Sam. I've got a couple of questions just to start off. And if any of our attendees have questions, you can either just type them into the chat or just put your name, and we can give you, then we can give you the option to just ask through voice. So first question is just with the hydromechanical systems, can you give any kind of idea of how much fall do I need to have to implement one of those?
Yes, that's a great question. And I have some notes to give you some ideas about that. So let me set up a scenario where you have, so a lot of center pivots operate on a quarter section. That's a pretty standard size. If you have that much flat land, that's about 125 acres. And the center pivot on that would be about 1/4 of a mile long to cover that half-mile long section, half-mile wide. So about 1,300 feet long, which is about 8 towers. Each of those towers has a motor on it that's about 3/4 of a horsepower. So you have about six horsepower total needed just to run the towers. Excuse me, let me get some water. So let's say the terrain is a little bit uneven as well. Typically in the mountains, you don't have a full quarter section, excuse me. So you might have a wiper configuration. So in addition, with that uneven terrain, maybe you need about 7.5 to 12 kilowatts to move that center pivot up and down hills. And so total for operating the whole machine of, let's say, between 8 and 12 kilowatts. So that's about 10 to 16 horsepower total power. Because all the extra energy all comes from the water as it's flowing to the center pivot. And let's say in that scenario, for if it is a full 125, well, you know, a 1,300 foot long center pivot, probably your flow rate is about 900 gallons per minute. So that's about 2 CFS. So going back to that equation I mentioned, 2 CFS, and let's see, so we need to know how much head, how many feet of drop is available, and then we can calculate how many kilowatts of power. So typically you need 30 pounds of pressure just to pressurize the sprinklers and get the flow through all the nozzles. Let's say you have an additional 40 to 65 pounds. So we're talking about 75 to 100 pounds of total pressure in your system. That's pretty significant. And projects like that are not too easy to find, but that would give us so we have about 95 to 150 feet of excess head, and we've got 2 CFS. So that gives us about 200 to 300 divided by 25. That gives us about 8 to 12 kilowatts of power using that equation to operate that system. So for the hydromechanical system, that's plenty of excess pressure to operate a center pivot with 8 towers on it. Or if we have excess flow instead of excess head, let's say we have just enough head available to run that center pivot to pressurize all the sprinklers with no booster pump or anything. How much excess flow do we need to power that pivot? Well, you need about 4.7 cubic feet per second of excess flow. So a total of about 7 cubic feet per second. And a lot of farmers are not going to find that very easily, so they can be challenging to find those projects. But those are, you know, that's one scenario where if you have about 30 pounds of pressure in your pipeline and about 7 cubic feet per second, or you have maybe about 65 pounds of pressure and 2 CFS, then you can operate one of those hydromechanical systems, or you can generate about 12 kilowatts of hydropower. Does that make sense?
Yeah. And then one question that we have in is, you mentioned the report that outlines the 5,000 irrigation systems
Yes.
in the fields. Where can we find this? And I'd be curious, how deep does it get in pointing out those systems?
Yeah, so that report, the contractor that put together that report, they used some geospatial data to identify all the irrigated fields, mostly across Western Colorado, but actually across the whole state. And then they used an algorithm that they created to find all the fields that had significant topography, a drop across that field. And wherever there were likely sources of water to irrigate those fields that had significant topography with them. And so based on that, they were able to say that based on this satellite data, we know where all these irrigated fields are, and these are the ones that have good potential for hydropower. But we don't know who owns those properties or so forth. So it gives us an estimate of the potential to develop more projects like this across the state, but it doesn't tell us how to go and find the property owners to develop those projects.
And was that report, is it the recommendations for developing agricultural hydropower in Colorado from 2013?
Yes. Yeah, so that it's on our website. If you go to colorado.gov/ag/energy, then there's a link to learn about hydropower, and you'll find it on that page. And thank you for posting that as well.
I think hopefully that link works, and that'll immediately yes, it does. It'll just download that document for you. Another question is, would the NRCS funding be available to irrigation districts?
So the way EQIP works is that EQIP contracts are always directly with the farmers and ranchers themselves. And the way it could be funded, or the way that funding could go through the conservation districts, is if, for example, the conservation district has a technician, like a soil technician or irrigation technician, who would provide technical assistance on that project. So many times they would have to be a TSP, I believe, a technical service provider registered with NRCS for the EQIP program.
I know in the recent farm bill that now EQIP can contract with water delivering entities. I haven't worked with anybody who's done that yet. I'm now talking with Mitch that's looking at just doing a piping project. Has that overlapped at all with this? Is that maybe a new opportunity to maybe contract with a district or a ditch as an entity?
Yeah, that's a good question. I haven't seen that yet in this program.
I know it's still very new. I'm still trying to track someone down who's actually done EQIP for anything with an entire entity. Yeah, so that might be an opportunity there.
So I'll just add, you know, if the conservation district does have an engineer who can design the, you know, put together the engineering on the center pivots and pipelines, we can pay them for the services that they provide, and in that way provide funding to the conservation district. And so.
All right. If we don't have any other questions, I think up there we're getting almost to our limit here. Thank you so much, Sam. I really appreciate it. We're going to be posting on our website and all of our member groups, and then it gets quite a bit of views. It just right now it's a really busy time of the year, and it's great to have this along. So this was a great program.
Yeah, great. Well, there was a lot of information there that I covered. I hope it wasn't too technical, and it's tough to cover so much information in an hour. I would love to have a full day if I could, and then we could dig into how to figure out which turbine works on an irrigation system, and you know, look at the specifics of how we engineer these projects. So we did, as part of this program, when we started 6 years ago, there were no engineers who could help us with this. And the first thing we had to do is create a technical manual that explains how to identify and do the engineering for these projects and how to do the feasibility studies. And then we trained about 70 engineers across the state. About half of them were NRCS engineers, and there were a few from the conservation districts as well. And those that technical manual is also available on our website. It's a little bit harder to track down. Maybe I can post a link to that.
And I'll be sending out links with all of this to the attendees, and we're gonna have some information on our website too.
Great.
Well, thank you again, Sam, and thank you for our attendees. We really appreciate it. And everybody, you can have the rest of your day.
Yes, thank you all. And please contact me if you have more questions.